Good morning. We are looking at chapter 8.4 today, looking at what are called intermolecular forces and then how they affect, or really how the types of bonding affects the intermolecular forces. So to begin with, the classic one that's studied, we've already talked about are water molecules. We know that that there's a polarity created, right? The oxygens don't share the electrons evenly with the hydrogens and create a net overall negative charge down near the oxygen, near the chin, and that the hydrogens have a net overall positive charge. And because of that, we have an attraction. And as it says there in what we're trying to do here is this helps us explain why we have for covalent substances, a relatively high melting point, right? 0 degrees Celsius, obviously, in our thinking is cold. But in terms of covalent molecules, that's a pretty high melting point. And then 100 degrees Celsius for boiling point, high boiling point as well for them to completely break free of each other. As we progress through this, we'll also look at the dissolving ionic compounds in water, making aqueous solutions. And then one of your labs for this chapter is on chromatography, which basically is the attraction or lack of attraction between substances in the liquid phase. Okay, so we begin by that, looking at the water molecule. Let's go to the next slide here. Some definitions that we need to have here. Number one is the intermolecular force is between two molecules. Excuse me, between two molecules. So we have that attraction, okay? Inside each water molecule is an intramolecular force. Now, there has been an AP question that asks something related to number one. Which do you predict to be stronger here, the intermolecular or intramolecular forces? The way they worded this on an AP question was something to the effect of like a theory, that like a student posed a theory that said when water boils, the covalent bond between the hydrogen and the oxygen breaks apart. And then they wanted the students to explain why this theory is true or not true. And of course, for full credit, you would be saying that is not true. It's the hydrogen bonding, the intermolecular attraction between the two different molecules is what breaks apart when we form the gas particles. We don't actually break the water molecule itself up. That's going to require a higher amount of energy. Okay, so, just be thinking about those kinds of things as we progress through this chapter and be ready for a test question that could be related to that. Then the second question that's here says, why are intermolecular forces unimportant in ideal gases? Okay, so one of the things we said back in chapter 5 with ideal gases is to be an ideal gas, the two gas molecules or two gas particles have to be completely unattracted to each other. All their collisions have to be perfectly elastic. There can be no attraction between them. So if there's no attraction between them in order to be ideal, then there can't be any intermolecular forces, right? So these have to be negligible in order for the gas to be considered ideal. And then one of the things we said is for real gases, that's when these things start to become part of an issue, is that the particles, when they collide, could actually stick to each other and form a bond. That's going to lower the pressure of the gas, because now if these bond to each other, two separate particles, even though now it's bigger, two separate particles have become one. And as one particle, then there's fewer particles inside the container. Remember, this for gases, the size of the particle doesn't matter. All right. Solvation. You've seen this picture before. We've seen this one a number of times. I always make the joke in honors chemistry that the sodium chloride crystal lattice is your ice cream, and the water molecules are the ants on the ground. And when you're going around licking your ice cream cone and you take too big of a lick and that ice cream plops right off of the cone onto the ground and you cry like a baby, you go inside, mommy gives you a brand new ice cream cone, and then you go back outside all happy and you see the ants have already started breaking down the ice cream, right? The water molecules do the same thing to the ionic compound. Sometimes for substances that are soluble, we have that the attraction, it's not necessarily that we would say the attraction of a oxygen to the sodium ion is stronger than to the chloride, but the fact that many water molecules are all going to be working to dislodge that sodium, and many ears are going to be working to dislodge that chloride, such that you can see here how there's a bunch of water molecules. Remember, this would be a three-dimensional picture. Can you picture this thing completely surrounded by water molecules? There's enough water molecules to keep this suspended in solution and not attracted to the sodium that has the same thing going on with its ion with the water molecules as well, okay? So it's picking it apart like so. It's a great picture to be able to analyze what's going on here between those two. Our types of bonds, and then therefore the intermolecular forces ranked from strongest to weakest is what you see here. And this list always makes me a little bit unsettled because of the amount of overlap that occurs here. And it's not just like gray area overlap that one thing could be stronger than another. It's that, like number 3, a covalent network could actually jump over some metallic bonds. So it's not even just jumping over the one above it or below it, it's jumping 2 ahead. So this is just a general rule of how we would rank our bonds. And I think that if you think this through, it kind of makes sense. Metallic bonds, you're thinking really, really high temperatures to melt a metal. Ionic substances, we've seen that, very high temperatures to melt them. Covalent networks, well, I mean, like diamond, that's a covalent network. We would actually maybe put that up with the metallic bonds in terms of melting and boiling points. Hydrogen bonding, that's going to be the topic that's coming up here, and how to separate that from polar covalent bonds. It is a type of polar covalent bond, but it's a little bit stronger most of the time. And then lastly, this makes a lot of sense, is the non-polar covalent bonds. How do you get 2 hydrogen molecules, 2 H2s, to bond to each other? How could you, we know that you probably want to cool down the gas tremendously, close to absolute zero. But eventually it does form a liquid or a solid. How do you get that to happen? So we need to explain non-polar covalent intermolecular forces can exist. We'll get to that in a moment. Looking at structures will be the next set of notes that we have here. Covalent bonded molecules have weaker intermolecular forces. We've already talked about that. Here's some pictures that kind of go with this. This one didn't show up as well as I'd like it to, but it's still the same water molecules that we had before. So this is the intermolecular forces between 2 water molecules. So it's partial charges attracting each other. Down here in an ionic compound, there's supposed to be pluses and minuses going throughout all of this, but it didn't look like the minuses showed up very well. Here we have the ion, the cation that lost the electrons. Here we have the anion that gained the electrons. So if this one's positive and this one's negative and this one's positive, 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 negative, 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 you can see that we end up with why we call this the crystal lattice, is because this is going out 3-dimensionally, and it's going, billions and billions and billions of ions that are there, and the attraction between them is a strong Coulombic force. And so therefore we would recognize that these should have higher intermolecular forces, means higher melting points, higher boiling points. But remember that the water, by virtue of a lot of water molecules, can work to wiggle out all of these little ions out of there and dissolve the ionic compound. Here's a good note. This goes back to that water molecule thing. The dipole-dipole interaction right here is only about 1% the strength of the bond that's right here, right? So the intermolecular, I probably should have said this on the last slide. The intermolecular force is only 1% the strength of the intramolecular force that's there. So definitely when we boil water, we're breaking the intermolecular bond, the dipole-dipole bond. We're not breaking the intramolecular covalent bond. Exceptions to which of the dipole-dipole interactions that are a little bit stronger, still weaker than the covalent bond, but stronger, are the hydrogen bonding in these 3 substances that you see here, which we see related to each other on a periodic table, which I think is what I have on my next slide, and there it is. So here's a graph from a textbook that shows how these 3 have higher boiling points. So see the boiling points listed here as our y-axis, and then we drop down to lower boiling point. So what we're looking at right now is these three have higher boiling points, and then I don't know if we try to group, then the lowest ones there are these, right? So we're looking at this grouping next. So highest, lowest, and then slowly start working their way up. So as far as a periodic trend goes, this didn't make the list because our periodic trend is weird. Our periodic trend is kind of saying that the boiling point increases as we go down. The reason for that is because the substances are made up of atoms that are getting larger and larger. So if you want to get a, like let's pick on hydrogen iodide right there. If you want to get the hydrogen iodide to boil or to melt or whatever else, see, we're looking at boiling points, so let's pick that. If you're going to get the hydrogen iodide to boil, you got to get that big molecule to wiggle enough to break free of the other ones. So in terms of wiggling is kinetic energy, remember that the formula for kinetic energy, temperature is related to kinetic energy, is equal to 1/2 mv squared. So a larger mass is harder to get it to wiggle enough where it completely breaks free of each other. So the downward trend makes sense, except for, but now we got to deal with the exception to the rule, the hydrogen bonding. So with these three, now what we have going on there is, even though they're really small, so put some energy in there and they move quicker. Our issue with them is they're so small. So the attraction, so back to our, let's pick on somebody new. We'll pick on hydrogen fluoride. So with only 2 energy levels around the fluorine, when the hydrogen and fluorine bond with each other and the electrons are spinning, and then high electronegativity also, but I can't use electronegativity as my explanation here, because then my problem is how do we explain why chlorine, which is pretty close to oxygen in its electronegativity, why isn't it included in the group of hydrogen bonding? It's really only those three that get to be classified this way. Because of the smallness of the fluorine, the next hydrogen over, these two can get really close to each other. So the dipole interaction between these becomes stronger than the normal dipole-dipole interactions of the rest of the groups. They get really close, right? So the proximity to this hydrogen compared to the proximity to this hydrogen, honestly, I don't know the difference. I have to still assume that this hydrogen's closer. Back to that graph of the potential energy with Coulombic force, but it's still really, really close, enough that this becomes a strong bond, stronger than, say, 1% of the strength of this bond. Okay, that's got to make sense, because hydrogen bonding is something that's always talked about. So that kind of hopefully explains the trends. If I didn't do you justice, pause this, put something from the internet, put something in here so that you can explain this, because this is definitely a crowd favorite for a test question. All right, so now our last thing is the non-polar covalent molecules. How do we get them to be attracted to each other is what we call London dispersion forces. All right, so what I've got here is 2 molecules. If you're looking at this online with my notes, there's great text boxes that explains all of these steps. You can follow that through if you want to. What happens is, in these 2 molecules, there's no reason for them to be attracted. The pair of electrons are being shared equally between the 2. Remember, this is like a hydrogen-hydrogen and another hydrogen-hydrogen. There's no reason for them to be attracted, right? There's no reason for there to be a dipole-dipole interaction, a plus and a minus, anything to attract them. But these electrons, by chance, can be found anywhere. So if by chance these 2 electrons happen to be found at one particular moment in time, and we're talking about a split second. Remember, what happens in the atomic world is going on at a rate that we can't fathom. A split second in time, they happen to be found on this side. If that happens, there is a temporary dipole that forms in molecule A, because the electrons are found on one side, just purely by chance. Now, that right there is an electric force. And just like when you take maybe a balloon and rub it against your hair and then bring it near your hairs on your arm, and you can feel your arm hairs stand up, the balloon's not touching your arm hairs, but your arm hairs know that they're there because the electrons are saying so. So the electric field is felt by molecule B, and its electrons will be attracted to this place where there's a emptiness of electrons. Remember, we're going to talk about Vesper theory coming up, that electrons want to do everything they can to be as far apart from each other as they can. Why we travel as a pair? Well, maybe we have to talk about that whole Pauli exclusion principle and having, one electron with spin up and one with spin down. It doesn't matter. Think of them as a pair. That pair is attracted to the empty space, creates an induced dipole, and then that looks like this. So how this is usually stated in a textbook or by a teacher, a temporary dipole induces a secondary dipole, and now there is a slight attraction between the two. Not a strong one, but there is a slight attraction, which can explain why we can actually get our nonpolar molecules to form bonds, right? Form solids, form liquids, rather than be in the gaseous state all the time. Chapter 8, homework number 4 is your assignment. Number 22 is super important. So don't just quit when you're doing the early questions here. Like if you get stuck on 18 and 19C and you don't know what those mean, move on. You have to get to number 22 because that is a crowd favorite for a test question. All right? All right, see you next time.